Good morning, everyone, and welcome back to day 2 of Forward CloudSec. Before we begin, just a couple of quick administrative notes. First, just a reminder, please take out your cell phones and make sure they're on silent out of respect for the amazing slate of speakers we have for you today. Second, we'd like to thank, as always, our sponsors who make all of this possible. In particular, we'd like to thank our gold sponsor, Tamnoon. So our first talk of the day, we have the good, the bad, and the ugly, hacking 3 CSPs with 1 vulnerability. This talk was put together by Halai bin Sasson and Andres Riancho. Unfortunately, Halai wasn't able to make it here today, but I'm sure Andres is going to have a great talk filling in for him. So please welcome Andres to the stage.
Thank you very much. Today, we're going to be discussing how we hacked into 3 different cloud service providers using a single critical container escape vulnerability. During our research, we identified this vulnerability in NVIDIA Container Toolkit, and we used it to hack into more than 10 different cloud service providers. Today, we are just going to be discussing 3 out of those 10. As my presenter just said, my name is Andres, and my co-speaker is Eli. Sadly, he was unable to make it, but we're both security researchers at WIS, and we specialize on cloud security research. We identify vulnerabilities in cloud service providers and also in open source software such as Kubernetes and, in this case, NVIDIA Container Toolkit. NVIDIA Container Toolkit is basically a container runtime that's going to allow you to run AI inference and AI training from within containers. NVIDIA Container Toolkit is responsible for configuring your containers in such a way that those processes can access the NVIDIA GPUs. You might not have heard about this software component, but it's actually very, very common. If you are running an AI service on the cloud, 90% sure you're running NVIDIA Container Toolkit. During our research, we found a critical container escape vulnerability. This vulnerability allows us to mount the host file system inside the container. This means that from within the container, we can read and write files from the host file system, and we can potentially interact with Unix sockets, which might also be in this host file system. The only requirement that you have in order to exploit this specific vulnerability was to control the container image. You had to either control the Docker file that's going to be provided to the service, or provide an image that you build with a specific Docker file. This was the dream vulnerability for us. We knew that NVIDIA Container Toolkit was used in almost every cloud service provider, and the exploit itself was very reliable. We knew that there was no way for this exploit to crash any of those services if it failed in any way. So we really believed that we had a chance to answer this question. How does each vendor handle a critical zero-day vulnerability? From previous research, we knew that every service is built in a completely different way. But in this case, we had the same zero-day affecting a ton of services. So we started our research and found between 10 and 15 different targets. We exploited the vulnerability, and today I'm going to be discussing just 3 of those case studies. These case studies are representative of what we found in all the research. First, let's start with Azure Container Instances. Azure Container Instances is a service provided by Azure in which you can provide your image and they are going to run that on their network, hardware, and so on. You don't need to worry about updating packages in the operating system. You don't need to worry about anything. They just run your image. Azure Container Instances has GPU access in preview mode, so we got access to that. And it was pretty easy to get the exploit to run. Almost no modification in our initial proof of concept. After the successful exploitation, we started a quick analysis of the host file system. What we found was that the host had around 20 container images. By inspecting the overlay FS, we were able to find that information in the host file system. We are interested in knowing why and how many container images exist in this host, because in our research, we aim to do cross-tenant access. And this means that we want to prove access to information from other tenants. In this case, and because there were only 20 container images, it doesn't look very promising for cross-tenant access. Next, on the host file system, we found the kubelet credentials. This proved one of the things that we wanted, which is that the host was a Kubernetes cluster. Then, using those credentials, we tried to gain access to the kube API, but due to networking limitations and security controls, that was impossible. Finally, in this initial analysis, we went through the host processes. Using the proc file system, you can read all the processes from the host, and we were able to just attribute those processes to different services running on the host. We were not finding processes from other tenants. Once again, well done, Microsoft, on the design and isolation here in the design of Azure Container Instances. But we really wanted to connect to the kube API. So we had access to the host file system, and because there was Docker sock, we could interact with that in order to create new containers. So we used the Docker CLI in order to create a new container in this host. And we used a special trick. We created the container in the same network namespace as the host. We did that because we know that from within the host, it's possible to reach the kube API. So the kubelet can actually reach the kube API. So we place ourselves in that same position in the network. That was successful. We were able to connect to the kube API, and using our credentials from the host, we authenticated successfully. Sadly, the get nodes command only returned one node. This, from the researcher's perspective, is something that we were not expecting. We had high hopes for finding hundreds or thousands of nodes, but that was not the case. This is very much aligned with what we saw before. So this doesn't seem to be a service in which we are going to be able to get cross-tenant access. We continued our research. We scanned the network. We did DNS resolution for the internal IP address namespace, captured traffic, but after 5 days, we just decided to label this use case, this case study, as no cross-tenant access. This environment was built for us. It was not shared with other tenants. And really well done, Microsoft. This is what we expect from a well-designed system. Next case study is going to be replicate. Replicate is an AI software as a service in which you can upload your models, and the community can consume them in order to do AI inference. So they can do text, audio, video, and so on. Multiple companies, such as Salesforce, OpenAI, and ByteDance, are using Replicate in order to share their models. When you want to share a model on Replicate, you need to provide a cog. A cog is basically a container for machine learning, but behind the scenes, it's just a Docker file with a specific entry point and a few customizations. Nothing really fancy, but we had to adapt our exploit in order to be delivered as a cog. This required 4 hours of research effort. After the exploitation, what we found was more than 500 container images. This is interesting for us and as researchers because it's a strong indication that many other tenants are running their workloads on this host. We were also able to identify the kubelet credentials. We found them and used them to connect to the Kube API. This is one of the differences that you're going to see between Azure Container Instances and Replicate. In Azure, we were unable to reach the Kube API from within the container. Here, we are able to do that. Finally, we listed the host processes and confirmed that some of those processes we could attribute to the host file system, to the host, and some of the processes were from other tenants running their workloads, their AI models. One of the processes that we found, and we immediately realized that this was interesting, was this one. Here you can see just a process, but one of the parameters is specifying a Redis URL. In that Redis URL, and it was redacted, of course, you see the password to connect to the service and the full domain and port. From previous research, we knew that this is a Redis task queue. So every prompt from users goes to this task queue, and then finally reaches the AI models. The same thing happens with the results from the AI models. They go to the queue and then go back to the user. So at this point, we could have connected to this Redis queue and perform different actions, such as reading the prompts, reading the predictions from other tenants. Also do some kind of interference by modifying them, deleting them, and so on. And this was possible for both public and private models on Replicate. But we were not interested in this Redis service because that was past research. We wanted to actually connect to the Kube API and expand within the Kubernetes cluster. We took a break, and we were figuring out with Eli what to do, and at some point, we received this. So in our screen, when we want to replicate, we saw your account has been temporarily disabled. We said a few things that I'm not going to repeat in public. And then we continued to, of course, we paused our research. And we started to figure out our next steps. 5 minutes later, I received an email from Replicate asking if we were doing research on their platform. We said many other things that I'm not going to repeat. And then we just stopped our research and sent all of the information to Replicate. Really great job here, Replicate, on identifying our actions in your network and taking your actions to disable the account and reaching out to us. The last case study is going to be DigitalOcean. In DigitalOcean, one of the services is called Paperspace Deployments, which is just like Azure Container Instances. You upload your image, and it's going to be run by Paperspace Deployments. The exploitation was successful. No special customization in the exploit was needed. And we performed our same 3 steps. The container images running on this host were more than 500. Once again, very promising, and an indication that this is a host that's running models for multiple tenants. Next, we found the kubelet credentials. These credentials were going to be later used, but the connection from within our container to the kube API was successful, no limitations there. The host processes also indicated that this host was running models for different tenants. We used our kubelet credentials in order to authenticate and run some commands. The first one that we ran was get nodes. And this was amazing. So we were able to get a response for that. And it was a cluster with 700 plus nodes. This is a pretty decent cluster size. The next thing that we did was to get the information for the pod of one of our test accounts. And this also was successful. We were able to retrieve the name of the image running in this pod and the name of the image pool secret. On Paperspace, when you provide an image that is in a private registry, from the UI of Paperspace, you need to configure the secret so that Paperspace can pull that image from your registry. So that's the name of the secret. And with our credentials, we were also able to retrieve the value for that secret. And we could have done this same thing for every other pod in Paperspace. So this could be considered a full service compromise. We started from a malicious container. That malicious container was pulled and by the cluster, by the Kubernetes cluster, a pod was created. Because of the container escape vulnerability, we were able to move into the node. And from the node, we used the credentials in order to compromise models, source codes, and secrets. The secrets in this case could be like the ones that I showed before, Kubernetes secrets, or secrets stored as environment variables within the images, or configuration files also. So this was a full service compromise, very different from the other scenarios. Summary and takeaways. So we had one vulnerability affecting the entire cloud ecosystem. This vulnerability was a critical container escape, and we used it to learn more about how different cloud service providers are building their offerings. This research had very different outcomes on every service. For Azure Container Instances, there was no cross-tenant access. We really, really tried. Nothing came out of it. For Replicate, we had access to the Redis queue, and we could have some modifications to the prompts and to the inference results, but the impact was rather limited, and our actions were flagged by the blue team, and we had to stop our research. Finally, DigitalOcean, we achieved full service compromise. The difference here is basically which security controls, guardrails, and best practices were implemented while developing and were implemented while creating these services. Securing your Kubernetes cluster is a very difficult task. And I'm not going to try to tell you how to do it in one slide and in 3 minutes. But if we have 3 things that we believe could have reduced the impact of this vulnerability, we believe that user namespaces, which is a new feature in Kubernetes, is really useful to reduce the impact of container escapes. When you use user namespaces, your pods are going to be run using a different user namespace, a different user ID than the one that you have on the host. That level of isolation is very beneficial to reducing and preventing some container escapes. Networking. As we saw in Azure container instances, it was impossible to reach the kube API from within the container. We believe that this is a network policy and a restriction that should be implemented in most services. So whenever possible, do that. Restrict access from your application or for the applications running on pods to the kube API. Sidecars and other components in your cluster still need that connection, but most likely the application running there doesn't need it. Finally, permissions. Many of the actions that we were able to perform on Paperspace were because the permissions associated with the kubelet were excessive. So for every principal that exists on your Kubernetes cluster, make sure that you use the principle of least privilege in order to reduce the permissions that you assign to those. Thank you so much. If you want to learn more about this specific research, we have a very technical blog post on the vulnerability, which can be found in wiz.io/blog. Most research content is going to go out in the next months. So just bookmark that and visit it every now and then. If you have questions, I'm all ears. Thank you.
Thank you very much, Andres. Just a reminder that we do have a question thread in Slack, so if any of you here don't ask them live, or anybody watching on the live stream, please put your questions there, and we'll go ahead and ask them. If you're here and have questions, please raise your hand, and we'll try to get to you. So.
Hey, I understand if you don't want to name names, but was there anybody that was as strong as Azure in this, and was there anybody else that caught you in any of those categories there?
Yeah, that's a good question. We saw other use cases, case studies, which were similar to Azure, maybe not as good. And no other cloud service provider detected us doing our research.
Right, so what sort of takeaways would you have for users of these services and ways that we can try to defend ourselves against this? Is it just trying to vet the providers to make sure that they have these controls in depth? Like, what would be the takeaways for our users?
That's a really good question. Because you don't really know how these services are going to be built. And they might have a really large investment in cybersecurity. And we saw that, for example, in some cloud service providers that have 2 or 3 different offerings for AI services. And one was very much vulnerable, and the other one was really well built. So it's difficult to really know what's behind the curtains.
Other questions in the room? I guess sort of one final question for me. So the underlying container toolkit vulnerability that you exploited, like how long did it take these? Did you observe for providers to patch that?
Their patch was actually pretty fast. In all these case studies, it took them less than 2 days to apply the patch, which is amazing, really, really well done in these cases. We didn't track all of the patching cycle for everyone, but in these 3 cases, really well done.
Right, we had a question from the Slack from Jay. Do you think cross-tenant workloads should be placed on separate Kubernetes clusters?
Ooh, good question. So we have a set of recommendations. We, as Wiz, has a set of recommendations and a framework on how to do exactly that. The name for that is Peach. So basically, if you want to learn more about how to run different workloads from different tenants, you should follow the Peach framework. We believe, as Wiz research, believe that containers are not strong isolation. So you could think about using micro VMs, such as Firecracker. Yeah?
Great. We're out of time, so please give one more round of applause to Andres.